This tutorial focuses on analyzing test questions on electromagnetism and electromagnetic induction. Our first question. A vertical wire carries a current straight upward. To the east of this wire, the magnetic field points A. North, B. East, C. South, D. Downwards. So, in determining the answer to this question, which is asking for the specific direction of the magnetic field that is induced, okay, in a current carrying wire, it all depends on how the directions, especially for the current, how it is described in the question. So it says that the direction, the way the vertical wire is positioned is such that the word straight upward means that the vertical wire is perpendicular to the surface of the earth, right? So if you're talking about such kind of direction, and then the use of the word east or eastward, okay, a point eastward of the wire suggests that we are going to use the geographic directions north, south, east, west. All right. So obviously, the way the vertical wire is positioned is that it is perpendicular to the surface, the earth, meaning the ground. Okay, so using our concept, Oersted's experiment, all right, which showed that a current carrying wire always induces a magnetic field around the wire, okay, as shown in the following illustration, all right. So we can determine the direction of the induced magnetic field by using what we call the right hand grip rule. So imagine that you're going to grip the vertical wire in this manner. So in doing so, your thumb, which represents the direction of the current, conventional current that is, all right, as indicated, the current is directed upward away from the ground. So your thumb is pointing upward in the direction of the conventional current. So that if you're going to close your four fingers, the other four fingers, or curl them, okay, the curling shows a counterclockwise direction, and that represents the induced magnetic field. So in general, we can say that for a current that is directed upward, okay, upward away from the ground, we can say that around this vertical wire, there is a magnetic field directed in a counterclockwise manner, okay? But since the question is very specific, asking for the direction of such magnetic field at a point east of the wire, meaning at this point, all right, at that point, all right, or using the other illustration, we are looking for the magnetic field direction at this particular point, which is some distance away from the wire. All right. So, since the overall direction of the magnetic field is circular, we can imagine that at that specific point, okay, the direction of the magnetic field is such that it is tangent, okay, tangent to that point. And if the wire is directed perpendicular to the surface, that would mean that towards that direction, right? You can imagine that is, if this direction here is east, and then the opposite, of course, is west. Therefore, the north geographic location or direction is in that direction, which from our perspective looks as if that direction, the north geographic, okay, is what we call a direction that is away from us or into the screen, away from the reader or into the screen. So, but from among the choices, that direction is best represented by the north geographic direction. So, that means our answer to this question is letter A. Question number 2. A current carrying loop of wire lies flat on a tabletop. When viewed from above, the current moves around the loop in a counterclockwise sense. What is the direction of the magnetic field caused by this current outside the loop? Take note of the word outside the loop. All right. Here are our choices. The magnetic field, letter A, circles the loop in a clockwise direction. Or letter B, the magnetic field circles the loop in a counterclockwise direction. And letter C, the magnetic field points straight up. And letter D, the magnetic field points straight down. All right, so this again requires us to use the concept of Oersted's experiment. But this time, instead of describing uh, a current carrying conductor to be straight, it is now uh, a loop or a circular loop. All right, so we can imagine that the current is moving through this circular loop. All right, so this loop is carrying a conventional current, and it is specified that such direction of the current is counterclockwise. So we need here an illustration again. All right, so based on Oersted's experiment, if that is the loop, all right, look at the way the direction of the conventional current is represented here. Supposing that this part of the loop, okay, is connected to a positive terminal of a battery. Okay, so we imagine that the conventional current goes like that, then around the loop in a counterclockwise direction, then goes back to the negative terminal of the battery. All right, so usually questions like this is interested to know the direction of the magnetic field overall, okay, inside the loop. All right, and as indicated by these magnetic field lines, these several arrows that you see, all right, represents what we call the magnetic field lines that is uh, produced as a result of the current, okay, through this loop. So for example, at this particular point around the loop, all right, you can imagine the magnetic field is directed, okay, in a counterclockwise manner. All right. Likewise, on this opposite end of the wire, we can also imagine that the same current is directed, but it's in the opposite direction. This is now clockwise. All right. It's only at the very center, middle, at that point, okay, where the magnetic field line is exactly straight up. Okay. So there is a catch in the question because of the use of the word outside the loop. So we are not pertaining to the magnetic field inside the loop, but instead we're talking about the magnetic field outside the loop. That's why the word outside in the question, okay, is underlined, okay, to give you a signal that that is not normally what is being asked. Usually, it is the magnetic field induced around the loop inside. No? That is what is most usually uh, asked in a lot of questions. But this time, we are talking about outside, okay? Such as, for example, uh, at this point, okay? At this point, what is the direction of the magnetic field exactly to the left of that particular part of the loop? So as shown by these circular arrows that you see here, representing the magnetic field, again, just like in the first question, you can imagine that uh, the instantaneous magnetic field at that point has a direction tangent, okay, tangent to the point in the circle, right? So that makes choices A and B already not possible answers because we are looking for an answer that is specifically tangent to that small circle, okay? But again, uh, the use of the right hand grip rule is now or has now been modified, okay? In other words, instead of what you call, instead of the thumb representing the current, okay, uh, the original right hand grip rule is such that the thumb represents the direction of the current in a vertical straight wire. But this time, since we're talking about a loop, circular uh, wire, uh, we will use our grip or our four fingers as we move around the loop. Okay, so the four fingers will will represent, okay, will represent the direction of the current as shown in this illustration. All right, so we imagine that the direction is going counterclockwise, and then outside that particular part of the loop, the one on the left side, again you can imagine, okay, uh, the current or the magnetic field being uh, directed again in a counterclockwise manner. That's on this side of the loop, but on the opposite side here, that's quite the reverse. All right, okay. You can also imagine that these magnetic field lines that are emphasized in this drawing, the ones inside the loop, all right. For example, this one. Actually, it's not shown anymore in the in this illustration, but each and every magnetic line here completes a circular loop. For example, this one. Okay, we can imagine that this is just part of the whole loop. Okay, okay, part of the whole loop that is circling this uh, this loop. All right, and again, just like what's shown by this arrow. Okay, at that particular point, it is tangent. Okay, tangent to that circle. So, what do you think is our best answer? Okay, to describe the direction of the magnetic field exactly outside the loop, not inside but outside. We say that it points, okay, straight down, okay, outside. It doesn't matter what you're talking about which outside, okay, which part of the loop outside it, okay, whether it is to the left or to the right. You will notice that the circular uh, the circles, all right, are pointing exactly downward. If you are imagining the tangent, the line tangent to the each of that circular loop, all right, it is tangent. Question number 3. The direction of the force on a current carrying wire in a magnetic field is described by which of the following? Letter A, perpendicular to the current and parallel to the magnetic field. Letter B, uh, perpendicular to the magnetic field and parallel to the current. Letter C, perpendicular to both the current and the magnetic field. And letter D, okay, the force, magnetic force, is perpendicular to neither the current nor the magnetic field. So this is a concept in electromagnetism, okay, that relates three important what we call quantities, such as the direction, or not only the direction but the magnitude as well of the current. All right, the current that is being carried by the by any conducting wire, conducting rod. All right, and we said that if this current carrying conductor is placed in an external magnetic field, okay, magnetic field is represented by capital B. It's a vector quantity. So the field, take note, the field we're talking about is an external magnetic field. This is not referring to the magnetic field induced in the wire. All right, that is very important. Okay, when you are talking about the uh, Fleming's equation or formula, okay, which relates the magnetic force that is acting on any uh, current, in other words, any charged particles, all right, uh, such moving charge, okay, will be experiencing a magnetic force F, okay, if it happens, if the charged particle happens to be in a magnetic field produced by an external source. For example, uh, a bar magnet. So a bar magnet is an example of an object that has its own magnetic field. And then if you're going to imagine that a charged particle enters such magnetic field, all right, it is going to experience a magnetic force. So the relationship of the external magnetic field and the current or the charged particle that is within the magnetic field will experience such force known as magnetic force. All right, and just like in the case of Oersted's uh, experiment, there is a need for us to describe the direction of the magnetic force produced. Okay, so we will uh, represent each of this quantity using again our right hand rule, but we don't call it anymore the right hand slap rule. I mean grip rule. I have my own way of describing it. Okay, so I'm calling it the right hand slap rule. This is how it goes. All right. So you open your right hand, okay, such that your thumb is or makes an angle of 90 degrees with your other four fingers. So in the illustration, if that is the thumb, all right, pointing upward, that arrow represents the direction of a positive charge or a conventional current. Now, the other four fingers, okay, will be pointing towards the direction of the magnetic field, okay, the magnetic field which is coming from an outside source, such as a bar magnet. Okay. Now, if you're going to uh, move your right hand as if you are slapping, all right, someone, if you're going to slap, okay, isn't it that the palm will be pointing towards a direction, okay, towards the direction of the person you are slapping, and such direction of the palm points to what we call the magnetic force that is experienced by the moving charge. Did you get that? Okay, one thing, very important. Such magnetic force should also be directed in a way that the angle it forms with the magnetic field must be 90 degrees. Okay, and likewise, the angle that is formed by that magnetic force with, okay, the vector arrow that represents, okay, the current, all right, although we are not considering the current as a vector quantity, we are in fact talking about the velocity, all right, the velocity of the charge, okay, is what is being represented by that arrow, all right. So we have here a case where the three vectors are mutually perpendicular. Okay, that is the best, what do you call, the best situation where we can expect the magnetic force to be at its greatest. Okay, each and every vector that we are talking about here, okay, is mutually perpendicular to each other. But if, for example, the angle is less than 90, okay, for example, the angle between the magnetic field, all right, and the velocity of the charge doesn't make a 90 degree, exactly 90 degree angle, then we just have to determine the component, all right, the component of the F, okay, that is exactly perpendicular to each vector magnetic field as well as the velocity. Okay, the formula that relates the three quantities, but it depends if what is given is, for example, in this case, you are given the current, all right, the current in the wire, all right, is what is described as uh, I. A letter I represents for the current, and the length of the wire is represented here by the letter L, and of course the B stands for the magnetic field that is coming from an outside source. So if you multiply the three, you will be describing the magnitude of the magnetic force. But supposing we have a case where the magnetic field and the velocity or the direction of the current is not perfectly 90 degrees, then we have to make use of the trigonometric function sine. We get the component, all right, the component that is perpendicular to the magnetic field. Okay, so we use sine of the angle. Okay, for example, the value of sine 90 degrees is already the maximum. So uh, using sine as the function, okay, we are getting the maximum value of the magnetic force. Okay, that's why always remember the term mutually perpendicular. Okay, supposing the wire and the magnetic field are exactly parallel, okay, that would mean that the angle between them is 180 degrees if they are exactly opposite, or 0 degree if they are in the same direction, parallel as well as anti-parallel. In either case, okay, the sign value will be exactly equal to 0. So that is a case where we have a situation where the magnetic force is equal to 0. So the maximum value for the magnetic force that you can obtain is if the angle we're talking about is exactly 90 degrees. All right, so already the answer is specified here as letter C, meaning that the magnetic force, okay, produced here is perpendicular to both the current and the magnetic field. We are only asked to describe the direction of the magnetic force. All right, but if questions will require you to quantify, then use Fleming's equation or formula, which is F equals BIL. There's another version of the formula, that is if it is the charge Q, all right, that is given. So the formula becomes the product of the magnetic field times the velocity of the charge, okay, and of course uh, the amount of charge itself. So something like F is equal to the product of B, V times Q. But for now, okay, this is what we are using as a basis to answer this question, sometimes called Fleming's formula or Fleming's law. Question number 4. A negatively charged particle moves across a constant magnetic field. The magnetic force on this particle, letter A, changes the particle's speed. Letter B causes the particle to accelerate. Letter C is in the direction of the particle's motion. Or letter D changes the particle's speed, causing the particle to accelerate. Alright, so our answer here is letter B. Why? Okay. Uh, if we look at our illustration, okay, we can imagine that the direction of the magnetic field, okay, is into the screen. That's why you see here the symbol cross or X. Okay, this X, several X's or crosses, represents the direction of the magnetic field that is away from the reader into the screen, right? And then imagine a negatively charged particle labeled negative Q entering this magnetic field, right? Originally, the direction of the motion of this charge supposedly is, as shown, it is to the right, all right? Represented by the velocity arrow or vector arrow for velocity that is directed to the right, all right? So, what's going to happen, okay, to this negatively charged particle? Okay, it's going to experience a magnetic force upon entering this magnetic field, and you can determine the direction of the magnetic force by using not the right hand slap rule, but we will use the left hand slap rule. All right. So with your left hand, again, we will represent the magnetic field. All right, with your four fingers extended. Okay, your thumb, which forms a 90-degree angle with the other four fingers, the thumb represents the direction of the velocity of the charge, in this case, to the right. All right, so position your left hand such that your thumb is directed to the right, while your other four fingers extended are directed into the paper or into the screen. You will notice that when you slap with your left hand, your palm is pointing towards this direction represented by the red arrow, meaning it is downward, okay, from our perspective. All right. Now, what if the charge is already at this point. Okay? Again, using your left hand slap rule, where the velocity is tangent, all right? That is where your thumb should be pointing, and then the magnetic field is still into the screen or into the paper. Again, your palm will be pointing towards this direction represented by the red arrow. So in general, at any point around the circular path, the direction of the magnetic force is towards the center of the circular path. And this reminds us of the concept of centripetal force. That is exactly the kind of force that is experienced by the negatively charged particle as it moves across a constant magnetic field. All right? That's why in our equation here, the force, which is equal to the product of the magnetic field B multiplied by the charge Q and the velocity B, can be equated to the formula for the centripetal force, that is the mass of the particle multiplied by the square of its velocity divided by the radius, capital R. In case you are going to calculate for the radius, then you just isolate R, and the equation simply becomes R equals mv divided by bq. Alright, so going back to our explanation why the answer should be letter B. Okay, we say that uh, throughout this motion of the negatively charged particle, its speed, okay, or the magnitude of its tangential velocity will remain constant. All right, so only the direction of the velocity is changing at all times. And because of that change in the direction of the tangential velocity, okay, we have what we call a centripetal acceleration. Right? The centripetal acceleration, of course, is or arises because of the net force brought about by the magnetic field. It is the magnetic field that's responsible for this centripetal force. Okay? By nature, it is an electromagnetic force. Okay? But since it's always directed to the center, hence the term centripetal force. Right. So, letter A in our choices, letter A cannot be considered correct because it describes that the particle's speed is changing. That is not what is happening. Okay. Uh, because in a uniform circular motion, we say that the tangential speed is always constant. All right. It is only the direction of that tangential velocity that is changing at all times, arising to what we call a centripetal acceleration. If the magnitude of the tangential velocity is changing, then we will also have what we call a tangential acceleration. All right? In which case, we will have already a net acceleration that is not exactly directed to the center. But that's again a different story. In here, we are only talking about uh, uniform circular motion, which is the effect of the magnetic field that is crossed by a moving negatively charged particle. So, that makes letter A, as I said, incorrect. Letter C, the magnetic force on the particle is in the direction of the particle's motion, referring to the tangential velocity. That is not correct because, as we said, um, the force F should always be perpendicular to both the magnetic field and to the velocity vector. And for letter D, changes the particle's speed. Again, that is incorrect because, as already described, the tangential velocity always has a constant magnitude. All right? That is the reason why option letter D cannot be considered correct. All right. So, uh, that explains why our answer, the best answer for this question, indeed is letter B. Question number 5. Two long parallel wires placed side by side on a horizontal table carry identical current straight towards you. From your point of view, the magnetic field at the point exactly between the two wires, A, points up, B points down, C points towards you, or D is equal to 0. So we are again talking about the concept of um, Fleming's law. Okay, right. So it says here that the answer is letter D, 0. Why is this equal to 0? All right. So we imagine, as described in the question, the two wires, okay, are such that they are positioned. Uh, we're talking about vertical wires, right? So the two wires are exactly perpendicular, all right, to this screen. Okay, that here represents the direction of the current that is towards you. Okay, the magnetic field is what we are looking for. The current is towards you. It says here, current straight towards you. All right, so I sub 1, this is the current passing through wire 1. Since the wire is positioned perpendicular to the screen, okay, and the direction of such current is towards you. And for wire 2, that's also exactly the same. The current is also directed towards you or towards me. Okay. Now, we are asked to describe the direction of the magnetic field exactly between the two wires. So I draw this, what you call, a circle that is broken circle, all right, or it's not a solid circle, which represents the magnetic field. Okay, so use your right hand, again, right hand, because we are assuming that the current we're talking about is conventional current. Okay, you try to grab or to grip the wire in such a manner that the direction of the current is represented by your thumb. All right, so at exactly to the right of the first wire here, right, to the right of this wire, you will notice that the instantaneous magnetic field is directed tangent. All right, tangent, because the magnetic field around this wire 1 is directed in counterclockwise direction. All right, that's the general description of the magnetic field B1. And at that instant, the magnetic field is directed tangent, all right, as shown by the red arrow. Now, how about for the second wire? In the second wire, use again your right hand, okay, in such a way that your thumb is pointing towards you, all right? So, that is the way the magnetic field, okay, is directed. Now, at that point, exactly at the center, okay, of the two wires, the instantaneous magnetic field brought about by the current I2, right, is directed tangent again but downward. So the blue arrow represents the instantaneous magnetic field of current I2, right? But we're talking about the magnetic field, total magnetic field, or the vector sum of the magnetic fields B1 plus B2. So, if the amount of current for each I1 and I2 is the same or equal, then it follows, and then that point there at the very center is equally distant from either wire, then we can generalize that the magnetic field also B1 and B2 are equal in magnitude but opposite, exactly opposite in direction, and so therefore the total magnetic field must be equal to 0. That's why our answer is letter D. Question number 6. The figure shows a magnet being pushed into a coil of wire which is connected to a galvanometer. Alright, so this symbol, electrical symbol with capital letter G, represents a galvanometer. Consider the following statements. Number 1, the induced current will flow from X to Y through the coil. Number 2, and Y will become a north pole. Number 3, the galvanometer needle will deflect to the right. Okay, so which statements or statement is or are correct? For letter A, it's only statement 3 that is correct. Alright. For letter B, it's only statement number 2. For letter C, both statements 1 and 2 are correct. Alright. And choice letter D, statements 2 and 3 are correct. Alright, so this is an example of a situation where we have what we call a phenomenon known as electromagnetic induction. Okay, induction meaning from the word induce. Current in the coil is only an induced current. What does that mean? So, supposing we have here a bar magnet whose north pole, all right, is on the left side. So, if you're going to move this bar magnet towards the coil of wire, all right, what's going to happen? There will be what we call an induced current. Okay, an induced current in the wire, and such current induced can be determined or can be indicated by how the needle of a galvanometer will behave. Okay, this red arrow represents the pointer, okay, of a galvanometer. So if this pointer deflects to the right, it means that the current passing through it is directed to the right. But when it deflects to the left, then the current is directed to the left. So, how do you determine the direction of the induced current? Alright, so we make use of, let's look at our concept and also the answer already given. It says that the answer is letter D. Both statements 2 and 3 are correct. Number 1 statement is incorrect. Why is that so? Alright, this is what we will apply. There is a law in electromagnetic induction known as Lenz's law. Alright, Lenz's law. According to Lenz, okay, if this bar magnet, remember a bar magnet has its own magnetic field. Alright, so the magnetic field of a bar magnet is outside the bar magnet is directed from the north pole to the south pole. You can imagine the magnetic lines to be directed, okay, away from the north pole and towards the south pole. Inside, it's going to be from south to north, all right? Those magnetic lines of force, remember, are complete loops, and they are not intersecting with each other, right? Now, the key concept, according also to another equally renowned scientist, Michael Faraday, okay, we can only induce current, okay, if the magnetic field is changing. If there is a change in the magnetic field, okay, there is a current that will be induced in this coil of wire. So that's the reason why we need to move this bar magnet towards the coil of wire, and moving it towards, okay, will not necessarily cause, okay, a strong induced current. There is a need to do it very quickly, all right, because the rate of change in the magnetic field is also a factor. How fast is the change in the magnetic field, okay, going to take place will also matter. The faster the movement of the bar magnet, okay, will cause, okay, a greater what we call induced current, okay, because the delta B, all right, the delta B or change in the magnetic field is done very quickly, right? If the bar magnet is not in motion, there will be no induced current. Okay, I hope you have done this experiment already in your physics class. All right. So, what we are trying to describe is the direction of the current in the coil when the bar magnet is being moved towards. So, where is Lenz's law here? According to Lenz, okay, if the bar magnet is being moved towards the coil, okay, it is as if the coil also becomes an electromagnet, okay, an electromagnet such that the end represented by Y, okay, becomes a north pole. Why is that so? Why not south pole? Because according to Lenz, okay, the induction is such that there will be a force that will oppose, all right, that will oppose the original action. What is the original action? All right, the original action is when you move the bar magnet towards the coil. All right, so there seems to be a force of repulsion that will oppose or that will counteract such movement. This is north. That north pole will be opposed, of course, not by a south pole, but by the same pole, north pole. Only between two like poles will there be what we call force of repulsion. So in doing so, okay, it is as if you are encountering, all right, you are encountering a force of repulsion as you are approaching, in moving the bar magnet, you are approaching the coil. So if you are the one doing it, you will feel some kind of opposition, meaning a repulsive force trying to prevent you from moving towards the coil. All right, that is exactly what the Lenz law is telling us. But you persist, all right, in overcoming such force. So you try to continue to move, and to do that, okay, you need to exert a force to overcome the force of repulsion. Hence, you will be doing a work. There is work done, okay, by an outside force. In this case, if you are the one moving the magnet, you are the one doing the work. All right. So, electromagnetic induction essentially is an illustration of the law of conservation of energy. Okay. Energy cannot be created out of nothing. Okay. You cannot do that. If you want to produce energy, okay, in other words, electrical energy in the coil, then you have to do work, okay, by pushing the bar magnet towards the coil. But in doing so, you will be encountering a force of repulsion such that the coil becomes a temporary electromagnet whose magnetic field, okay, as an electromagnet, the coil becomes an electromagnet, so it has its own polarity. The Y becomes north and the X becomes south. All right? So, with that description of the magnetic field inside the coil, we can determine how the direction of the induced current will be. All right? So, using your grip rule once again, your right hand grip rule. Okay? Try to grip this cylindrical, what do you call this? The cylindrical or rectangular object here is an object that you need for the wire to be wound, all right, around. Okay, so it is something that can hold several loops of wires. And usually what is used here is a material that is made of iron, all right? An iron bar or an iron rod, because as we all know, an iron rod is a good material, a ferromagnetic material whose ability to maximize, all right, the amount of magnetic field that is created as a result of the changing magnetic field from the outside. Okay, so again, the magnetic field of the electromagnet, meaning the coil, is directed to the right from X to Y. So use that, represent that magnetic field with your thumb. Remember to use the right hand. So your thumb represents the magnetic field. As you curl your forefingers, okay, okay, notice how the wire is being wound around the rod. Okay, it is wound in such a way that this particular coil, for example, is over the top. All right, there it is. So you can imagine that the curling of your forefingers represents the induced current. Hence, we can imagine at this particular part of the coil, the current to be moving down. I'm talking about this particular coil. All right. Now, how does it move when it passes through the galvanometer? Right. We say that the current moves from left to right, making the pointer in the galvanometer move or deflect. Okay, it will deflect to the right. So there is a sudden deflection that can be seen, okay, in the galvanometer, indicating that there is an induced current detected by the galvanometer. That makes statement number 3 correct. All right. And as far as the current induced in the coil, it is directed, all right, not from X to Y, but it's from Y to X, making statement number 1 incorrect. All right. And as earlier mentioned, end Y of the coil will become the North Pole. That's correct. Hence, our answer indeed is letter D. Only statements 2 and 3 are considered correct. Okay? So, this phenomenon, let me emphasize that once again. This is a simple illustration or example of electromagnetic induction. Whatever induced current is produced here depends on such factors like the number of turns, all right, of wire in the what do you call this? In the iron rod. If there are several turns, that will increase the magnetic field induced. Also, the amount of change in the delta B, all right? The amount of change in the delta B, meaning to say the rate of change will also determine the amount of induced magnetic field. And another thing, the size or cross-sectional area, the cross-sectional area of the coil, okay, which depends on the radius of the coil, will also be a factor. All right. So what I'm saying is, according to Faraday, the amount of induced voltage is also called the induced EMF. We can represent EMF as capital V for voltage or EMF, that is equal to the change in or delta, okay, delta phi. Delta phi is actually what we call the change in the magnetic flux. And a magnetic flux is simply the product of the magnetic field and the cross-sectional area, okay, of the coil. So, the bigger the radius of the cross-sectional area, okay, the greater is the delta phi. Okay. In our succeeding questions, we are going to illustrate that uh, amount of EMF that is induced. Just hang on because there's a question that will apply that formula of Faraday. But right now, okay, we have explained the answer why letter D is the best answer using Lenz's law. Okay, an equally important concept in electromagnetic induction. Question number 7. A generator produces 60 amperes of current at 120 volts. The voltage is usually stepped up to 4,500 volts by a transformer and transmitted through a power line of total resistance 1.0 ohm. Find the number of turns in the secondary if the primary has 200 turns. So we are given the choices: letter A, 5 turns, letter B, 200 turns, letter C, 4,500 turns, and letter D, 7,500 turns. All right. So, the concept about transformers is just actually the result of electromagnetic induction, okay, which we have briefly talked about earlier. Okay, first we will identify the given variables or data. We are given the current in the primary coil, okay, which is 60 amperes, and the voltage in the primary coil is 120 volts. The number of turns in the primary coil is 200 turns, and also the voltage in the secondary coil is at 4,500 volts with a resistance of 1.0 ohm. And then we are asked to find the number of turns in the secondary coil. All right. So the concept of transformers, okay, depends on the fact that uh, the power, okay, power actually, electrical power is the product of the voltage times the current. All right. So P is equal to VI. We know that. We are assuming that the transformer is an ideal transformer. We will ignore, okay, any form of um, energy that is lost in the process, which includes thermal energy. So an ideal transformer is far from reality. But for simplicity, that is what we will assume. That's why we are able to come up with an equation that relates the voltage in the primary and the voltage in the secondary coil, okay, in terms of the number of turns in the coil primary as well as in the secondary coil. And this is the formula: Bp over Vs is equal to Np over Ns. In other words, the number of or the amount of voltage that is induced in a given coil depends on the number of turns, right? They are directly proportional. That's why we are able to come up with this relationship: Bp over Vs is equal to Np over Ns. All right? Since we are given those values for Bp, Np, and uh, what else? The number of turns in the primary. So all we need to do is transpose this equation for us to be able to calculate for the number of turns in the secondary coil. And that becomes Ns is equal to Np over multiplied by Vs divided by Vp. Okay, each of these quantities, okay, is given, such as the number of turns in the primary, which is 200, multiplied by the secondary voltage, all right, 4500 volts, then divide this by the voltage in the primary coil, which is 120 volts, that will give us the result, which is 7,500 turns. All right. Uh, to some students, upon reading the question, they might be what we call this. They might wonder why other variables or other quantities are given, such as the resistance of the power line in the secondary. Okay, you have there the 1 ohm, but actually, okay, in this problem, there is no need to consider that resistance, because after all, we are given the quantities that we need to be able to calculate for the number of turns in the secondary. All right. So sometimes in a problem such as this, there are some data that are given as way of distracting uh, yourself. All right. You might be you might be tempted to try using other calculations where you are going to use the given resistance, but there's no need to do that, because all we need to find is the number of turns in the secondary coil, which can be determined in terms of the number of coils in the primary, as well as the given voltage in the secondary and in the primary. Okay, so it is very simple. The problem is very simple, but sometimes it becomes quite difficult, because you have the tendency to make use of the other given data, which actually are just distractors. So our answer here is letter D, 7,500 turns. All right. Question number 8, which is our last question. A circular loop of wire with a radius of 12.0 centimeters and oriented in the horizontal XY plane is located in a region of uniform magnetic field. A field of 1.5 Tesla is directed along the positive Z direction, which is considered upward. Now, letter A, if the loop is removed from the field region in a time interval of 2.0 millisecond, find the average EMF or voltage that will be induced in the wire loop during the extraction process. And letter B, if the coil is viewed looking down on it from above, is the induced current in the loop going to be directed clockwise or counterclockwise? All right, this in reference to the earlier question that we discussed. Okay, in other words, the concept behind this is Faraday's law of electromagnetic induction. All right. So in Faraday's law of induction, the formula to determine the induced EMF or voltage is just expressed as V equals negative N multiplied by the change in the magnetic field multiplied by the cross-sectional area of the given loop. Okay, sometimes the product BA is also called the magnetic flux, represented by the Greek letter phi. All right, so that will be divided still, by the change in or interval of time. Okay, you will notice that delta BA over delta T represents what we call the rate of change in the magnetic flux. Magnetic flux, by the way, is usually expressed in the unit Weber. All right. If the magnetic field is expressed in Tesla, that's the SI unit for magnetic field. If you multiply that by uh, an area in meters squared, then a Tesla multiplied by meters squared will actually give you a magnetic flux equivalent to a Weber, right? So in here, since we are looking for the EMF that's induced, by the way, the negative sign here again is just to emphasize what Lenz's law, okay, was explaining earlier, we said that the key word in understanding Lenz's law is the word oppose. Okay, so there will always be some kind of an opposing force. Okay, a force that seems to contradict, okay, the original action responsible for the induction to happen. So that is emphasized by that negative uh, notation, negative. So if we substitute now, we are talking only of a single loop, okay, just one loop. Therefore, our capital N is only one. Now, the change in uh, magnetic flux, which is the product of magnetic field and the cross-sectional area, all right, is now shown here. The given magnetic field is 1.5 Tesla, and the area, cross-sectional area of the loop, which is understood to be a circular loop, is just pi r squared. So, with three significant figures for the value of of phi, all right, we have 3.14 multiplied by the given radius already in meters, 0.12 meters. That still has to be squared before you divide it by the time interval, also already expressed in second. Okay, what was given was or is 2.0 milliseconds, so that's equivalent to 2.0 to the power negative 3 seconds. So if you do your algebra, you will get this value for the induced EMF, negative 34 volts. But if you are just after the amount of voltage induced, we say that it is equal to 34 volts. All right, in answering letter B, question letter B, we are asked to describe, okay, the direction of the induced current in the loop, whether it is clockwise or counterclockwise. So we can imagine that in our diagram here, all right, the source of the magnetic field is a bar magnet, all right, whose direction of the magnetic field, okay, of the magnet is directed up, all right, directed upward from the north. Okay, remember, outside a bar magnet, the direction of its magnetic field is directed from the north going to the south. So, we position the bar magnet like this. It is as if the magnetic field is directed upward. Alright? And then we imagine a loop, a single loop, whose area is along the, what was the description? It is oriented in the horizontal XY plane. Alright? So, imagine that this circular loop lies along the XY plane, whose direction to the right, of course, is east or X, and uh, what we have is into the into the screen represents the positive y-axis. Right? I hope you can follow. Because we already assumed that the magnetic field is upward. Okay? But that magnetic field is actually perpendicular. Alright? Perpendicular to the xy plane. Hence, we imagine that the east or x direction is to the right, okay, while the positive y direction is into the screen. Now, how do we find out if the current induced in the coil is clockwise or counterclockwise? So again, we make use of our right hand grip rule, modified rule, where the curling of your forefingers, okay, the curling of your forefingers will represent the current induced, and your thumb points in the direction of the outside magnetic field, which we earlier said is directed upward. All right, upward. Now, what will happen uh, if the coil of wire is extracted, meaning is removed, all right, from the magnetic field. It's only doing that where there will be an induced magnetic field and therefore an induced current. Remember, there is no source of uh, what you call no source of power. You don't see any battery here whatsoever. But by moving either the coil or the magnet, okay, we can come up with an electromagnetic induction in the coil. But it is the coil that will be moved. How? We are going to move the coil in such a way that we are trying to move it away from the magnet. Okay, the magnet is considered fixed, so its own magnetic field doesn't change. Okay, but the mere fact that you're going to withdraw, all right, or move the circular loop away, so it is as if, okay, the induced current will behave in such a way that, all right, the loop will have its own magnetic field that is opposed by the bar magnet. Okay, in short, you can imagine while the coil is being moved upward, that is indicated by this arrow, moving the loop upward, okay, we will have a case where such motion of the upward motion of the loop, okay, will result to a magnetic field, okay, a magnetic field wherein the direction of the south, okay, the polarity of the magnetic field induced in the coil is such that, okay, what is pointing, okay, to the bar magnet is the south pole. All right. So when you do, because we need to have something like, according to Lenz's law, something that is trying to oppose. All right, something that seems to oppose uh, the north pole of the bar magnet. All right. So if you're moving the coil away, there must be some kind of attractive force. Okay. Only an attractive force, okay, will sort of oppose this action of moving the coil upward. Hence, we need to consider that the induced magnetic field in the coil is such that you are, as you use your right hand grip rule, okay, your forefingers are pointing to the direction of the current induced, which in this case should be counterclockwise, right? Counterclockwise because your thumb will be pointing upward, okay? The thumb is directly pointing to the north polarity of the coil, all right? And opposite to that is the south pole. So the south pole of the coil, okay, exerts an attractive force with the bar magnet. You see? That's where the Lenz's law comes in. Lenz's law states that there must be some kind of an opposing force. Okay, it states that the opposing force between the bar magnet and the coil. Since you are moving the coil away, it is as if the bar magnet is trying to prevent the coil from being moved upward. And the only uh, kind of force that will, okay, exist is an attractive force between the north pole of the magnet and the south pole of the coil. Okay? So with that in mind, you can now use your grip rule. As you point your thumb, all right, as you point your thumb upward, okay, your forefingers will be representing the direction of the induced current in the coil, which of course will be counterclockwise. So we have answered question in letter B for this conceptual question number 8. And we are done with this tutorial. Thank you very much again for your indulgence.